Okay, now we're speaking about NavStar GPS system. NavStar means navigation system with time and range in global positioning system. So it's a satellite-based radio navigation system that gives us information on position, but also on time. It's also used to have time information, clock information. So we are speaking of 4 dimensions, 3 for the positioning and 1 is the time. It has been developed by the Department of the Defense of the United States in 1973. At the beginning it was a military system. This is the thing that every student told me, oh, it's a military system. Yes, it was born as a military system, but now it's used for civil application, really. With the President Clinton, they stopped to protect part of the signal, GPS signal we are going to see, and now it's really free. Of course, all the secret of the signal are secret of the development, but it's really free for everyone. In fact, now everyone that have a smartphone can know its positioning all over the world, for instance. The aim of this system was the real-time positioning with a precision less than 10 meters. So in this course we're going to see how to use this navigation positioning system to obtain information that can be used for geophysical interpretation. So for us 10 meters is too much, and we are going to see that we have seen in a previous lesson, we have seen that we can obtain information or record the sight velocity of some millimeters, and some application we can record very small deformation. So, but when it was created for real-time positioning for our smartphone or navigator in the car. It was developed for the military to know the air position everywhere in the world. But now we really use for real-time geolocalization, or what we call now geolocalization, real-time positioning. And this has to work also with vehicles that are moving in a fast way and under any weather condition. I didn't tell you about the traditional techniques for positioning is that you need to see the line of sight, to see the point that you are going to measure. And so it means that you don't have 3 objects between the 2 points, but also that often you cannot perform measure during the night or with bad weather condition, with fog or something like this. GPS is work everywhere and with any weather condition. Of course, we have to see the satellite. So if you have in a cave or in a gallery or in a very dense forest, probably we have no problem. We are sure that we cannot track the satellite. But this is a very specific condition. If it's raining or if we have fog, we can know our positioning. We are going to see why. The GPS component, this is a very classic approach to the GPS. The GPS is composed by a space segment, a control segment, and a user segment. The space segment are the satellites, the control segment are the special stations that control the system, and the user that are us with some antenna. This is a geodetic antenna, and with some receivers. This is a receiver very for sport, for tracking. So, but we can also use a more complicated receiver or our mobile phone. We started from the space segment, the GPS constellation. The satellites are placed in almost circular orbit, divided in 6 orbital planes with a well-defined distance, orbit inclination for each plane, 55 degrees. And all the systems were created, were developed to know the position all over the world. And to know the position all over the world, we see that we are going to see that we need at least 4 satellites. So the position of the satellite and of the orbit place are studied to be able to see at least 4 satellites all over the world. And okay, the orbital period is 12 hours of sidereal time, of 11 hours and 56 minutes for the local time. So it means that we can see the same satellite that pass over our head twice a day, but with a delay of 4 minutes more or less. So it means that over the time we change the satellite. We don't see always the same satellite over our head in the same time, but it's changing, but the satellite configuration change. And satellite, how many satellites we need? To be sure to have a first satellite available, they put the thing that the developer thought that we need at least 24 satellites active plus 4 spare. Spare mean if you have problem with satellite, we can replace this satellite with another one. Now 30 satellites. I have to check. I'm not sure that there are 30 satellites, but I want to show you that if one satellite, we told you yesterday, every satellite have a lifetime. But if a satellite is working without problem, then the satellite continues to work is in the orbit. So in some period we have also 30 satellites. Probably now we have more satellites. I read news in a technical newspaper that in few days ago, 5th of January, they put in orbit a new GPS satellite. It's the new one of a new configuration of satellite, because all satellites, also the technology is improved in this period. So we have satellite of block 1, block 2, block 3. It means that it's changing the technology of the satellite, the instruments, the frequencies that are using, the number of frequencies that are using, and so on. So a new satellite now started to work a few days ago. GPS is a one-way ranging system. This is really important. So we receive signal by the satellite, but the user cannot send information to the satellite. Of course, why? Everyone at the moment have a mobile phone, and it's impossible that everyone on the world send information to the satellite, and it's impossible. So it's a one-way ranging system. The satellite send us information. We are not able to communicate with the satellite. We just receive information. There is the definition of the sidereal time is the hour angle of the vernal equinox. Okay, I think that you can read and try to understand. There are different definitions of time. It depends on the application, the precision that you want. It's just to, if you ask what is the sidereal time, I put some information and a figure. Okay. I need to go to the core part of the system. Each satellite has an atomic oscillator on board of cesium rubidium. Because the clock is the core of the system, we need to generate temporal signals with a very high stable precision. Okay, from the figure you can see solar panel, because we need we provide power by the sun, and on board there are also battery, because when the satellite is behind the earth and cannot see the sun, you need to have sufficient power to continue its work. And each satellite has a propulsion system to correct its position, and this correction is controlled by the control segment that we are going to see. Okay, the control segment is a network of stations with different tasks. They have to determine the GPS time system. They have to know to compute the satellite ephemerity, the position of the satellite, and they have to check the behavior of the satellite clock. They can command some movement of the satellite to put in the right position or something like this. And we have different stations. For instance, Colorado, there is a master control station. That is the most important station, and there are other stations with different tasks. But okay, it's just to control if the system is working, and to predict the position of the satellite on the clock. The user segment are the GPS receiver, and we receive the signal from the satellite. It's a one-way system, of course, and a receiver. We have very different type of receiver. Probably I put I put a slide. We have the core is an antenna. We need an antenna to capture the signal coming from the satellite. In some system, you cannot see where is the antenna. It's like a microchip, and you cannot distinguish the antenna by the other part. For the geodetic application, it's really clear where is the antenna. It's a bigger, not so big. It's like more or less like this, 20 centimeters. More or less, is you know where is the antenna. The antenna is connected to a small computer called receiver. Is a receiver. In the receiver there is the software to collect the data obtained by the antenna to give us for information or real-time positioning, for instance, and to record all the observations that you need to know your position, and also you can use also to have other information. This is, for instance, for surveying, but also for geodetic application. You can antenna, receiver. Sorry, there is a mistake. And control is like a computer to talk with the receiver. Is used often when you have to organize your session of measurements and so on. If you are measure different point, you want to give a name of each site and other information. As this type of instruments that are used for cartographic, but also geological. Some of you are geologists, and when you can perform some surveying, you can use a GPS to record the information that you are collecting in the field. For instance, it's not to have information about the crust deformation, but just to put a label to the data to the information that you are collecting. So after you can use these labels, this geolocalization, to put in a geographic information system, a GIS, a system where a database with also that can deal geographic information, geolocalized data. Sorry. The signal. The GPS signal. Okay, on board of the satellite there are 4 atomic oscillators. Why 4 atomic oscillators? Because they can check each other, and if you have a problem, oscillator can work another. This is happened with the Galileo satellite. They put in orbit a set of, I don't remember how many satellites, and I realized that there was a problem, a technical problem with some of the clock on board of the satellite, but they realized this when the satellite was in the orbit. You can imagine the huge quantity of money that you spend. Fortunately, on board of the satellite there are more than 1 atomic oscillator, so the other one can replace the one that doesn't work. Now I don't know if they try to repair or they substitute the satellite or use it until it's working. I don't know. Okay, for the atomic oscillator produce an electromagnetic signal with a given fixed frequency. The frequency, the fundamental frequency, is 10.23 megahertz. So we are using frequency in the radio wave of the electromagnetic spectrum, especially using the L band of this frequency. Starting from this fundamental frequency, we have 3 types of signal. We have what we call the carry signal, L1, L2. We have codes, and we have message. We are going to see what are these. The carry are our, we have our original carry at a given frequency that we are going to see. We use, in the original, we use just 2 carries. Now Galileo is using 3 carries, and also the GPS system is improved, adding another frequency. So we can see like this carry as a fundamental signal, and you will have a pseudo-random noise code. They mean a code that is a pseudo-random, means that is changed after a long time. So if you look at a part of the sequence, it seems like random numbers, but it's just because the period of the signal is very long. And you modulate this carry frequency with this code, and you have the modulate carry. This is the core of the signal, this modulate carry. And we have 2 carries, L1 and 2. And the difference is obtain, multiply the fundamental frequency with these 2 terms. And we have 2 different wavelengths. The L1 have a wavelength of 19 centimeters. L2 have a wavelength of 24 centimeters. And we have another carry starting this time. Now, so they started to put in orbit satellite with another more frequency. And in this page you can have a lot of information about the modernization of this signal, because also the GPS started to improve the system and produce this is called modernization. this L5 frequency carry is used just for civil application. They produce another signal just for military application, but it's not a problem for us. Okay, we produce code. Code is this binary code with a pseudo-random noise. It's like pseudo-random noise. So it's a binary sequence of +1 or -1 signal. And we have different type of code. We have the C code or clear acquisition that have this frequency, and this code module just a L1. It's a civil code for civil application. We have the P code called precise code, and with this type of frequency 10.23 megahertz, and a period of more or less 38 weeks. So for this reason, it's a very long period, and we can call this code pseudo-random code. This code modules the signal, and we are going to see that it's fundamental to perform our measure, especially for real-time measurements. And is also each satellite has a portion of the code lasting 7 days. If each satellite has have a different portion of this code, we can identify the satellite. We receive we receive signals from different positions in the space, and we are going to see that we need to know the satellite that send us this information, because we are going to see in the equation that is important, know from which satellite is arriving the signal. And using this code, I can identify, the receiver can identify the satellite. There is an M code, military okay, is a new signal, is added in the modernization system, modernization of the signal. It's a code that could be autonomous, means that the user can calculate their position just using this M code. Otherwise, the P code is on the both frequency. So, but it's not important for us. This it's just to say that also in the modernization of the system, the GPS, they separate the civil application by the military application. So for us, we are free to use the system in the complete system. In the past, they use a system called Anti-Spoofing option. They can corrupt the signal. It was difficult to use in real time GPS observation, but it was just at the beginning of the GPS. In a few years, they realized that with this type of corruption of the signal, also the military have problem to compute their position. So they removed this because the military have a low-cost instrument, of course. And so at the moment we have really separated the civil part by the civil application by the military, so it's not a problem for us. We have also another code called message, and the message is important because in the message there is the information about the ephemerides, the position of the satellites. They are computed by the control segment, sent to the satellite, and the satellite, using the message D, send this information to the user. And this is very important to have real-time positioning. And there is also information about the health of the satellite. if there is like a flag, if you can use this observation or not, it depends if the quality of the working of the satellite, and also information about the satellite clocks. So the total signal sent from each satellite, taking into account just L1 and L2, are the carry L1 with this frequency, modulated by the P code and the D message. Okay, L2 is modulated by the P code and the message. So it's an electromagnetic wave, so we can represent it like a sinusoidal signal, of course. Okay. So, how we can compute our positioning? So we have the Earth, so we have a receiver on the Earth, on a boat, on a little island in the ocean, and this is our reference system, that is a geocentric reference system, and we have satellite and a receiver. What we do is we measure, we are going to see how, the distance, the range between receiver and satellite. We are going that how we can measure these distances, but now I focus just on how we can obtain our position. So what we don't know is, for instance, the Cartesian coordinate of the receiver, x, y, z. But what we know are the Cartesian coordinate of the satellite. So, in some way we can measure the travel time to obtain of the signals that start from the satellite and arrive to the receiver. And from this measure we can obtain a measure of the distance, because if we suppose that we know the propagation velocity of the electromagnetic wave, of course. So, if you look at this equation, we have three unknown parameters, x, y, z of the receiver, R. And to solve this, we measure D. And to solve it, we need at least three equations. So we need at least sorry, I shift. So we say that we have three unknowns, so we need three equations. Before to see how to solve this system of equation to obtain the coordinates, we are going to see before how we can measure this distance. We can perform two types of measure. We can have two types of observation, code observation or phase observation. The code observation is related to this binary code that module our signal. The phase observation is based on our carries. Okay, because code measurements observe the range. We are able to measure the travel time of the signal that arriving from the satellite thanks to the code. If we know this travel time, we are going to say how, and we multiply this for the light velocity, the velocity of the electromagnetic wave, we obtain the distance, this in theory, the distance between satellite and receiver. So this measure has been done correlating two signals, the signal arriving from the satellite and the signal produced by the receiver. So the receiver is able to produce a signal similar to the satellite signal. For this reason, we cannot use a random code, but it's a pseudo-noise random code. We need to know the sequence because the receiver has to reproduce this signal. But what happened? When we switch on the receiver, he receives signal from a satellite. In that moment, the receiver starts to produce a signal equal to what he received. But this signal is a shift in time. It started from the beginning. But when the signal arrives, is after some time by its beginning, when it start from the satellite. So we have two signals that are similar but are shifted in time. So if you correlate these two signals, it means that you shift in time the two signals to correlate them. This shifting is give you the time between the satellite and the receiver, the travel time. So satellite signal generated by the receiver is different, and we shift the signal back to correlate the two signals. In this operation, we measure the time. So the code are like some flag in the carry to recognize the carry, because the carry is a periodic sinusoidal signal. So we don't have any information about the time. It's a periodic signal. But if you put a code, it's like put flag along this train, this wave. So we can recognize the point, and we can obtain this measure of the time. Okay. Okay, but we are measure of time. We have electromagnetic signal produced by the satellite with a very stable clock. And we have clock inside our receiver, but the quality of our clock is not the same of the quality of the atomic oscillator on board of the satellite, of course. It depends also by the instrument, by the receiver. Good geodetic receiver have a good clock, but the quality is not the same. So we are doing time measurement. So we have a problem of synchronization of the clock. So we have a scale, a GPS time scale, controlled by the control station, the master station, the Colorado station, that gives the GPS time. We have clock on the satellite, and the difference is very stable, a good quality, and the problem related to the synchronization is not so high. But we will have also to synchronize our receiver time with this satellite and master control station. So we have a problem of synchronization. So we needed to put some offset, some correction to the time. So we have the time of the receiver, the time of the satellite, and the correction to the time of the receiver and the time of the satellite. Okay. Due to the high quality of the atomic oscillators on board of the satellite can be considered synchronized. We are going to see that for very high precise application, we take really we control also this quantity. But for the receiver not. And we see that just an approximation on 1 nanosecond could introduce an error in the distance equal to 30 centimeters. So when you use no good satellite clock, we have to correct for this error. So we have seen that for the receiver clock, the synchronization error is bigger than 1 nanosecond. Is about 1 millisecond. So this corresponds an error of 300 kilometers. So we cannot use the system if we don't consider this synchronization error. So we have seen that in the equation of the distance, our measure, of the coordinates. We say that we have 3 parameters, so we need 3 equations. To be for this problem, we have to introduce another parameter, so the clock error. So we have four parameters, and we need 4 equations. This is the reason because the GPS is studied to see at least 4 satellites. We need to correct the error, the synchronization error between the clock of the receiver and the satellite. Just one, not with each satellite, because we have seen that the satellite have a good clock, so can be considered synchronized, so the error is small. But so it's just one error of synchronization that is equal for all the satellites for this type of application, real-time application. So in the equation we have the pseudo range. We can pseudo range the distance corrected for the clock. Okay, and plus other error, we put this term means that we have also other error that we are going to see in the next lesson. This is all the quantity of the previous equation, the distances, the synchronization error, and so on. So for each observation epoch, the unknown parameter are 4. This is true for real-time positioning. We are thinking how the development, the people that have created this system. The problem was, in real time, I want to know my position, even if I'm moving and so on, in everywhere in the world. In real time, that means that I press a button and I want to know, it's some few minutes for the computation, I want to know my position. In real time, if I'm moving, I have to know time by time, epoch by epoch, my position. So we need to estimate 4 parameters, x, y, z of the receiver as synchronization error. So we need 4 equations. Okay, it's the same, it's a redundant information. So this is a pseudo range, and we need 4 satellites. We have to add another satellite, this one. Okay. Yes, in many receivers we can record the observation, and we can process the observation later when we arrive in your office, and you can process data. So in this case, if you don't have if you have a fixed point and you don't have 4 observations simultaneously because you have an obstacle, you can overcome the problem of the synchronization using more epoch, more observation. But if you are fixed, of course. So it means that you need you need at least for observation for real-time positioning. If you don't want real-time positioning but post-processing positioning, it's okay, because for instance you collect data for a geological application to geolocalize your survey. Probably you can come back in your office and process more data. You say, okay, this is the point where I found the free phase of the fault, for instance. I want to know the coordinate. I can stay a few minutes with my GPS, collect data, and I use more observation to compute my position that is given again from the unknown parameter plus this correction. But I have more observation, because what happened is that we receive not in continuous, we receive signal, as the signal is sent continuously, but we can record it at a given, we have a given frequency in collecting data. In the past, for instance, for geodetic application, we use 30 seconds Every 30 seconds we recorded a data observation, or every 20 seconds, 10 seconds. Now we increase the rate, and we use also 1 second or less, because we have seen that with the GPS I can have information also with the seismic form in case of earthquake. So we improved the technology, allow us to improve the rate frequency behind the Earth, and so on. So these are the epoch where I have data, and if I don't want the real-time positioning, I don't need real-time positioning, I can use more observation. I hope to don't confuse you with this observation. Okay. There is an empirical rule that gives us an estimate of the precision. We have two codes that model our carry, and we have two different precision. If we have there is a rule that says that the precision in the measure of the range is equal 1–2% of the wavelength of the signal used. So if we use this code CA, coarse acquisition, that have a wavelength of 300 meters, we have a standard precision, theoretical precision, at least 3–6 meters. With the code that use a wavelength of 30 meters, we have a precision of 30–60 centimeters. So there are theoretical values. This means that if you real-time positioning, you don't expect to have a position with a better precision. So when you use your smartphone for geolocalize yourself in a map in a city, it seems very precise, but it's not so precise. It's just that you see your position in a map. It's due to the scale effect of the map, of course, of the representation. And also you are in a map, so the system tries to force you to stay, if you are in a car, along the road, not outside the road. In fact, when you take a new road along your travel, the system for a victor try to force you to stay on the road. After he say, okay, you are outside the road, okay, and he started to draw your path without the main road. Okay, this is a theoretical precision, so you can see that with the P code it's difficult to perform geophysical observation. In fact, we don't use this type of observation for the geophysical application, but it's important that you know the basic of the system, also to understand the term, because in the receiver often you can read this term. Also in the file that you are going to process data, you can see P code, C code, and so on. And you can use this type of observation for geolocalize point, your benchmark, your geodetic monument, your geological survey, and so on. So it could be GPS can also use as a tool in surveying in the field, not only for deformation monitoring. The other type of measure that you can do is a phase measurement. The phase measure allows you to compute the distance between satellite and receiver. It's a more complicated, and we are going to see. When I switch on my receiver, the receiver can record the fractional part of the phase of this carry, just a fractional part. And from this moment we start to count the integer number of cycle. So we are speaking about periodic signal. Okay. Okay. We are speaking about periodic signal. So sinusoidal signal, because it's electromagnetic wave. So we can draw at the time t0. We recorded with our receiver the fractional part of the phase, these values, and after we count. Is not so symmetric. The number of integer cycle, 1, 2, and so on. So we add to this quantity the number of integer cycle. Sorry, I put in a. So we measure the fractional part, we start to count this number, and this number takes into account for the movement of the satellite. Okay. And if we multiply the phase for the wavelength, we have a measure of the distance, of course. But what we don't know is when we receive this, the real distance between receiver and satellites, it will give by this fractional part that we measure, plus this quantity, and that we don't know is the number of integer cycles between satellite and receiver at time t0, when we switch on the receiver. When we track a satellite, we don't know this quantity. After this moment, we started to count the integer cycle. Okay. So at the moment we have this problem. We don't know in this measure that give us the distance, we don't know this quantity, the integer number of cycles. That is called ambiguity phase. So we have the fractional part, we start to count the integer, and but the total phase is given by this measure phase plus the ambiguity phase. That we don't know. It's like when you don't know this part, the dashed part. It's like when you have a clock, this clock without a arrow, the arrow, the small one for the hour, and okay, I was out of the room, I came in, and I say, okay, we have just an arrow, no, sorry, repeat. Now I go out, meantime I was go out, one arrow stopped to work, we don't have, and it's broken, it's cancer, it's fall down, okay. And when I came back, I don't know how many times it's passed from when I came out and I came in. But for this moment, I look, okay, I say 12:05. So I can start again to count the time, looking at the integer cycle, and one of us have to watch the clock and count 1 hour, 2 hours, 3 hours, and so on. But we don't know the time before. It's more or less the same problem. So, if you look at the equation that we had before, now we have the unknown of the satellite coordinate, the x, y, z coordinate of the receiver, and for each satellite, we have another unknown parameter, the phase ambiguity. For each satellite, because each satellite is in a different position in the sky, in the space, so we have different number of integer cycle. So the number of So what do we have? If you look at for satellite, as you have learned from the code measurement, we have 4 equations, but the number of unknown in this case at least 7. 3 coordinates for ambiguity, 7 unknown. So we have a number of equations insufficient to solve this problem. But what is, how we can solve this part? We solve this problem thinking that the ambiguity is a constant value. It's the values that we have at time t0. After is a constant value. We started again to count the number of cycles, but that values was fixed over time. So we can solve this problem using observation coming from different times, from different epoch. This means that with a phase measurement I cannot perform real-time measurement. But for instance, I need at least 2 epochs to compute my observation. In fact, okay, at epoch 1 we have as unknown x, y, z of the receiver, and if you see for satellite, I'm going to draw. And 1, satellite 2, satellite 3 and satellite 4. These are the solar panel. Okay, these are our at time t0. Sorry, we can write epoch t0. We have as unknown x, y, z, zeta, n1, n2, and 3 and 4. The ambiguity coming from this satellite. At time 1, we have x, y, z, r, and 1, and 2, and 3, and 4 are our unknown. But in number equation are 4 equations. So we have 8 equations with 7 unknown. To be honest, I have to introduce also the delta t, the clock error. So we have 8 unknown. The clock, the synchronization error. So with 2 epochs, I can use a phase measurement. It's not so easy. In fact, for real-time application, is not used. To be honest, now we can use phase measurement, but we have to connect one receiver to another receiver. There are different techniques that allows us to have our position, but it's not used for navigation. Navigation need to really know the position, not to wait information coming from other receiver or other systems that help us to know where we are. So in the past I studied different techniques to improve the real-time positioning using phase, but it's okay, our techniques especially used for topographic surveying. It's not important now. Okay. We can also have what we call cycle sleep, an interruption in the signal. We say, okay, we started to count the number of integer cycle, and we start 1, 2, 3, 4, but we can stop this count because there is an interruption in the receiver, in the tracking of the satellite, because if I am in a city, one big truck between my and the satellite and so on, or I'm moving too close to the building and so on. So we have what we call a cycle sleep, and if there is a small stop in the tracking of the satellite, I can repair with statistical techniques this cycle sleep. The software that processes GPS data can deal with this cycle sleep, this interruption in the signal. But if we have an interruption for a long time, usually we introduce another unknown. We start again the computation of the unknown parameters. It's like an ambiguity. We have to introduce another unknown. So the number of the unknown increase. Okay. The same empirical rule that we have seen for the code measurement can be applied also for the phase measurements. And we have that the 1–2% of the wavelength, I remember that the wavelength were 19 or 24 centimeters. It depends on L1 or L2, in which carry we are using. This standard deviation is 2–4 millimeters. So you can see that the phase measurements are more precise, and it's the measures that are used for geophysical application. Now in the next we see that this is a theoretical precision, and this we can reduce this precision because we have to reduce this precision because we have to take into account for some error, from some problem in the measurement. But we also see how to reduce this error and how to solve the problem and have a good precision in the position. Okay, this is now this is a video, and okay, we have talked about GPS clock, and most of us are physics, astrophysics, and mathematics, so it's important to see. Probably we are thinking about relativity when we speak about 4-dimension, position in time, speaking about electromagnetic wave and so on. Probably you have seen about what's happened with the theory of the relativity. So there is a good video that that I found in YouTube that explain how the theory of the relativity is important in the GPS measurement. So